Here we are going to study WRC 107 calculation in detail. Okay. So we'll start with very basic shell theory. What is this shell theory? Okay. Let us take a small unit length part of a cylinder. Okay. Its length is unit, thickness T. Okay. Now on this part, okay, we have N force, which is force per unit length. Okay, because it's a unit length, which is what we have covered. So there is some force acting in the perpendicular direction. Okay. Also, there is moment. Okay. Definitely, if force and moments are there, that means there is some external load or internal load acting. Does not matter either it is internal or external. So there are force per unit length present at the cross section. Okay. There is also a moment. Now, if these both are present, how we can do addition of these two items? How we can add moment and force which is acting in the perpendicular direction, N and M? How we can add? Okay, that is what you're going to see, because of loads, you will not see only a primary stress getting generated in the perpendicular of the surface. There also be some bending moment getting created. So if there is bending moment, how we do the addition of these two? Okay, that is what first we'll see, the normal theory. Then on this theory itself, WRC 107 is best. Okay. So if you understand this theory, other part will become easy for you. Now, if I tell you to calculate the cross-sectional area, which we are highlighting here, okay, this cross-sectional area, can you give me the value of this cross-sectional area? All the dimensions are written, unit length 1. Any dimension you can consider, the unit mm or meter, whatever you want to take. What will be the area? So Harshad is saying L into T. Where is L or 1? So basically it's 1 into T, that means T. Absolutely right. Okay, everybody is absolutely correct. L into B, Subham, is nothing but L here is 1 and B is T. Okay, so basically area is T. Okay, now if I tell you to calculate the moment of inertia on this cross section because of M, like if this is a plane, and if any plane is there, if you have to find that area of moment of inertia for this part, how you can get that? T into cube by 12, T cube by 12. Okay, great. Force into perpendicular distance. Yeah, that is moment for Neil. Okay, that is the moment. We are talking about moment of inertia for this cross section. Moment of inertia is the property of that cross section. So it has nothing to do with what force or moment acting. Okay. Anjali Verma, TQ12, absolutely right. See, what is the moment of inertia formula for a rectangular surface? BHQ by 12. Okay. Right. I hope you know that. The TQ by 12. That will be the, I think most of you got it absolutely right. TQ by 12. That will be the moment of inertia of this cross section, which we have indicated. Okay. Now, if I have to find the stress due to membrane force, means with the force N, because of N, what will be the stress generated on this cross section? Can you tell me? Because of N force, what will be the stress getting generated? Formula is already written. N is N. Okay, only you have to divide that with area, which you have already calculated. Anil, absolutely right. Himanshu, absolutely right. Area, which we already calculated, and N is the given value. So N by T. Yeah, absolutely right, Vasif. So force, which is acting on that surface, divided by the area. So area here is only T. So the stress due to membrane force is N by T. Okay. Now, we will find the stress due to bending moment. How we find stress due to bending moment? If you remember this formula, this we studied in strength of material subject way back when we were doing engineering, maybe the first semester itself. Yeah. M into Y divided by I. Yeah. Yes, very great formula. Yeah. Sigma B is equal to My by I. Can you now tell me what will be the bending stress? M is already given. Y is what? Aleem has got it absolutely right. Y is nothing but T by 2, because Y is the distance from the center, okay, to the extreme point. So T is the total length. From center, if you want to take the distance from the neutral axis, absolutely right. That will be T by 2. Okay. So Sanjay Sharma is absolutely right. So I we already calculated TQ by 12. And only here we wanted to know is Y, that is T by 2. Okay. So that is the sigma B, right? Now, once we have the bending stress, try to visualize that bending stress. Okay. If we just try to draw it, okay, the bending stress will be like, okay, let me just take a different color. Yeah. So bending stress, let's black. Yeah. So bending stress will be like, this is the value at the extreme. At the center, it will be 0. And then at the bottommost, it will be in the opposite direction, right? Hope you remember that, bending. Any cantilever when we did, right? If, I'm considering that it's bending like this, the top is getting tension. So there will be the extreme force. And then it will slowly go down to become 0 at the center. Then again, go into the compressive direction. Okay. So, and what will be the behavior of the first one? The membrane force, that will be exactly equal across the section, right? Equal across the section. So now what we have to do basically, because of moment, there is stress generated in the same direction, and also because of membrane force. So what we have to basically do now, we have to just add them, right? So combined stress will be nothing but sigma M, the membrane force, plus sigma B, bending stress. So this will become my total stress formula, for adding both these items. Guys, clear till now? Anyone lost till here? I hope you're clear to this point. Asif is saying yes. What about others? Aleem, thank you. Thank you. Thank you. Great. So hold on. Now, till now, we are not touched WRC 107. Okay. Now, we are coming to 107. So if you see 107 general equation, if you open 107, you will see this formula. Sigma I is equal to Kn Ni by T plus Kb 6 Mi T square. Are you able to relate what we did and what is the formula given in WRC? Yeah, most of you might have already, to simplify, see, Kn and Kb are, constants which depends upon the actually stress concentration depends upon the ductile or brittle behavior of the material. So for ductile materials, they are just one. So Muhammad, you're saying that K is small element, but Kn and Kb becomes one for ductile material. In that case, now is it matching? If we take Kn and Kb as one, very close, right? If you remember the formula. Only thing I indicates the direction. Okay. When we calculate it in a particular direction. If you see in terms of cylinder, there can be several directions, like circumferential direction. There can be even longitudinal directions, completely 90-degree perpendicular to it, right? So I represents the direction. Okay. So we need to find the stresses in different direction. That is the reason I is coming. Okay. Great. Now for ductile material, we saw Kn and Kb1. So this equation, we can write it as Ni by T, 6m by T square. Exactly what we got. Membrane force, the stress due to membrane force plus stress due to bending. Both are summed. That is the equation for 107, and everything is based on that. Okay. Now, let us try to understand. Till now, very easy. Okay. Now, we'll be calculating stresses at 4 points. Okay. 2 on the longitudinal and 2 on the circumferential. We'll come to that. Now, see if this cylinder and nozzle joint, if I take a plane in the longitudinal, how the cross section will look like. Is it clear how this cross section will look like? Yeah. So the points which we are talking about, forget about 2 arrows which are indicated. That depends upon if there is pad or there is no pad. Okay. So what we are talking about is the stress, at, let me just indicate for you, at this point in the longitudinal ring. Can you see that arrow? At this point. Okay. And at this point. There will be upper and lower point, because due to bending, there will be positive and negative stresses, right? For membrane, it does not matter. It will be uniform across the section. But for bending, there will be upper and lower points. So that is the reason you see AU and AL. The second point will be coming at completely opposite, BU upper, B lower. So these are the 2 points which we are interested, and there are also 2 other points. If I cut this cylinder by a plane in circumferential direction, but completely 90-degree to the longitudinal plane, then my cross section will look like this. Easy. Again, 2 points. AB we have already taken. C and D. 2 points. So remember, A and B are in which direction? In longitudinal direction. Okay. C and D in circumferential plane, we are getting that. Okay. So first 2 points, A and B in longitudinal plane. Second 2 points in circumferential plane. Okay. It's important because, it will get added and it will become much more interesting if you, go forward. So A, B, C, and D. Okay. So in top view, just to make it clear, longitudinal plane, we took 2 points, A and B. In circumferential plane, we took 2 points, C and D. Yeah, 4 points. But upper and lower, as if it becomes 8. Okay, if we divide them in upper and lower. Thank you, Muhammad. Okay, great. So now 4 points are there. Basically, if we just 8 asif, because 4 plus 4, in all the upper and lower, 4 at upper, 4 at lower, 8 points is our area of concern. Okay. So A upper, A lower, B upper, B lower, C upper, C lower, D upper, D lower. Okay. Now, there will be several loads coming, but let us look at them one by one. What is this load? What is this load? Axial. Okay. Correct, Muhammad. Axial load. Axial or radial, whatever you say, sometimes we call it axial, sometimes we call it radial. But what you have to understand is the direction. Okay. Now, if this is the load, can you see how this behavior of the cylinder or sphere will be there because of that load? That is what is illustrated in this. It will try to compress it. Okay. If we see what types of stresses are getting generated because of this load, only because of P, there will be membrane stresses and also there will be bending stresses. Both the types of stresses will be generated because of this P. Okay. How to calculate, what will be direction, we'll see. Okay. Don't worry about it. If we see in this cross section, okay, P is the radial or axial load, and because of that, there will be stresses generated, both bending and also membrane. Right now, sign convention. For sign convention, you don't worry if you don't understand, because WRC has already given the sign convention for all these loads. When we are calculating this, you will see a table. In that, sign is already mentioned. Based on the formula, we have to just find the value and put it there. Okay. But to make you understand how that sign came, we have made that also, that how the sign convention works. So if you talk about this point, the radial nozzle, see, remember, we are talking about only one load till now, radial load. There will be other loads. We'll talk about that also. Don't worry. Okay. So this is the point. On it, if it is in circumferential plane, there will be 2 points like C and D. So if you talk about membrane force, it will be compressive in nature because it's trying to compress. Remember, it was pointing towards the nozzle. It was trying to compress it. Okay. So the behavior of membrane force will be compressive at C and D, both in the circumferential direction. Okay. If we talk about bending, once we talk about bending, there will be 2 points coming. You'll notice that when we talked about membrane, there was only C and D, because for membrane, it's uniform cross section. What is at the upper, lower also same stress will be there. But once it's bending, there will be DU and there will be DL. So upper and lower. So if you just refer, this diagram, it will be pretty clear that inside will be seeing tensile bending. Upper side will be seeing compressive bending. Just you have to feel, imagine how it's happening, and based on that, the sign convention is given. You don't have to even bother about the sign convention because it's already there in 107 for all the types of load. Okay. But still, to just make you visualize, we have taken this. Similarly, for CU, compressive bending at the top, and at the bottom, it will be, at the lower, it will be tensile. Guys, clear till now? Yes. Great. All clear. Thank you. Great. Now, let us see the moment. Like if I have a circumferential moment, then how that stress will behave. For radial, it was really easy to visualize. But now let us see about circumferential. This is also very easy if you just, try to visualize. Do you agree it will behave like this? Do you think because of this moment it will behave like this? Yeah. Great. So again, stresses generated because of MC bending moment will be first membrane stresses and also bending stresses. Both the two types of stresses will get generated. Okay. If you see in this cross section, it will look like this. Because of circumferential moment, how it will not be shear, Himanshu. Okay. Because of this shear, we'll talk about when it will be only because of torsion, MT. Okay. MC and ML and also P will not create any shear. Okay, so hope you're able to visualize this. MC trying to bend. So finally, if we take these 2 points C and D, for membrane stress, there will be only 1 point. There is no upper and lower. Okay, so tensile membrane, and other side it will be compressive, right? Because it's trying to bend like this. So one side it's tensile, the other side it's compressive, simple. Okay. If we talk about bending, upper it will be tensile, lower it will be compressive, so negative. Similarly, in the other side, upper compressive because now it's trying to bend. So Cu will be compressive bending and Cl will be tensile bending. So this is the bending. Now, local loads. What are the difficulties? Two we understood. One is radial and the second we understood is MC. But there are lots of other loads. What are these loads? First one, we already saw, radial. What is this load? The second yellow, this one, anybody can tell? Circum what? There is moment also, there is force also. Circumferential force. Okay. So this is actually the circumferential force because it creates shear. So we call it circumferential shear load. You can also call it circumferential force. Okay. Now this one, this will be easy now. Yes, VC and VL, longitudinal shear load. This will also create shear. Okay. The blue color, this one, what is this force? The blue one. Be careful, MC or ML. I can see both, but again, this is the same moment which we discussed just now. So it's circumferential, MC or ML. Okay, now people are saying MC. Great. It's MC, circumferential moment. Now this one, second blue color. This is ML. Now you're getting it how the nomenclature is given. So if you understand, many times people get confused to, because client has given in some other terminology and you have to input in some other terminology. So if you understand what is ML, what is MC, you will not have any problem. Okay. So MC, circumferential moment, and ML, longitudinal moment. Okay. Now the top one, this one, Muhammad is saying bit confused about what. Okay. If anything is there, we'll talk about shear because it will create shear. If you try to just visualize, yeah. So Vivek is saying torsion. Absolutely right. MT, torsional moment. Again, it will create shear. Okay. So why I'm saying shear? Because it will create shear in nature. At this stage, even if you want to call it as circumferential load, it's okay. Okay. But if you understand how this load will create which kind of stress, then you can, even call it as shear. So whichever forces we have called it as shear load, that will create only shear. There won't be membrane force we discussed earlier. There won't be a bending stress, which we discussed earlier. So membrane force and bending moment will be because of what? Can you tell me? Can you summarize which all among these nomenclature will have membrane force and bending? Yeah, Muhammad, yeah, it's easy if you just say load, but now we are going into little deep. So that is the reason, we have mentioned that. So again, I'm repeating one question. Please, all of you listen. Among these nomenclature, P, VC, VL, MC, ML, MT, which one will create membrane forces and bending stresses? One is axial, okay, P. Apart from that, MC, yes, and also ML. Okay, so these are the three: P, MC, and ML. Apart from that, VC, VL, and MT. These are the loads which will create shear. Okay, great. Now let us now we know the different loads. Now let us talk about how that stress we calculate. We saw the general formula also. Now let us try to come back to that. So we are taking the radial or axial load. Okay, P. So we know that it will create circumferential membrane stress, and also it will create circumferential bending stress. It will also create longitudinal membrane and also longitudinal bending. So 4 types of stresses it will create. Okay. Now, just to simplify to you, circumferential membrane, let me use a different color. Circumferential membrane and longitudinal membrane. Okay. Circumferential membrane will be acting where? Which is having the direction in the circumferential. Longitudinal membrane will be having direction in the longitudinal direction. Okay. So if you remember the membrane force formula, there was I. I was for direction. So the same formula, if I use for circumferential, the same formula will give you the stresses in the circumferential direction. If I use the direction as longitudinal, it will give the longitudinal. Don't worry, we will calculate it. Okay. We will see a little detail also. Don't worry. Okay. So now these 4 types of stresses will be there. Now, how we'll find this? Okay, so before finding, let us see about other loads. So P, we saw these 4 types of stresses will be getting generated. Because of VC, what will be getting generated? Circumferential shear. That is the reason we called it as only shear stress, shear load. VL, longitudinal shear. MC, again, will have all the 4 types of stresses, membrane and bending. ML will have all the 4 types of stresses, membrane and bending. And because there are 2 different directions in which we are finding, that is the reason circumferential and longitudinal. Okay. Why we are finding in circumferential and longitudinal both? Anybody can reply? Because of ML, we are finding stresses. No? In 2 extreme points we are finding. One in longitudinal and one in circumferential. Why? Why not only one? Anybody can tell? You'll get the answer later on, but at this point, I want to know. Why? Yeah, there will be different value of stresses, nature of application. We cannot know which one will be problem making. Please remember, we have to add these. These are what? Local loads. So we have to add them in the stress which is already there. Primary membrane PM is already there. You know what we are calculating here as a membrane is PL, local stress. That is the reason it's called local analysis. Why that general load PM is already there? PM is because of what? At all the points which we are trying to calculate, there is stress already existing. Forget about secondary, Himanshu. PM is actually primary stress. If I'm saying, even though there is no local load, this nozzle loads is not there, still that PM is there. Why? From where that already stress is coming on all the points. Internal pressure, absolutely right. Okay, so that is already there, and you know that in circumferential direction, it is twice than the longitudinal. Okay, and we have to add, we don't know which one. See, P, the stress in the circumferential is twice, but I don't know which local load will be more. It may happen that the local load in longitudinal is more, and if we add that in the longitudinal stress, it may become more. We don't know. So we'll have to compare them and add them separately to get the stresses. Okay, getting it, guys? So because there are already loads, already stress, this vessel is already under stress. Okay, there are local stress which are additional to that. Okay, so I need in all the directions so that I can accumulate, I can add the stresses in all the direction, and then I can compare. How to compare? We'll see. Okay, so now ML we saw. MT is only torsional. Okay, now let us dig deep how stress is we calculate. So if we take the first one, circumferential membrane stress, I want to find because of this radial load. How I will approach? Okay, what will be my approach because of this circumferential membrane stress? Okay, we have already seen one formula, which was actually this one, the second one, Ni by T 6 Mi by T square. Okay, now if you see the left hand side formula, which is like this is derived from the same formula. Why? What WRC committee has done is that they have found a relation between this, the circumferential membrane stress and the radius of that cylinder. No, so this they have already found a relation, and based on that they have drawn a graph, okay, for different loads and different radius by varying. This is the experimental part of this calculation. Okay, so the main formula is because of analytical. Now this constant, which we will be getting directly from the figure. Okay, other part we already know. Okay, if you consider that this part is given by somebody, this part, we already know the radial load, we know the radius, we know the thickness. So if this constant is known, Kn is anyway ductile material, it is 1. So our job is done, right? We will be able to get the stress directly. Okay, so that is what we will be doing. So how it is same, that is what we have indicated. Like if we just cross this P and Rm, finally you will get N phi by T. N phi is nothing but phi is the direction. Circumference is what we are indicating. Circumferential direction we are indicating by phi. So N phi by T. Okay, if you see, it's very exactly same. Only the I is the direction, which is here is phi. Guys, are you getting it? till now. The same equation from which we started, very basic general equation. That is what we are carrying till now. So radial load, how we are finding? Little bit twisted so that there is a constant. Okay. This n phi, which is already available in terms of graph, and other parts is already available with us. So we'll be able to find the stress. Okay. Now, so like I said, n phi P by Rm is a dimensional membrane force, which we can get from a figure. We'll see how to refer that figure also. Don't worry. Now, as we said, because of this P, there will be stresses in both longitudinal direction also, and there will be transverse axis also, right? Because if we see this phi, okay, phi is circumferential direction, and if we change it to L, it will become longitudinal. Okay. So in both the direction, we can get the value of this dimensional constant. Figure 4C will give you the constant value for longitudinal axis, okay, at point A and B. Figure 3C will give you for the transverse axis. So what we are talking about, how to find that constant, okay, which we saw in this, right? This value, how to get the dimensional membrane force, how to get that. If you want to find in longitudinal, we get it from figure 4C. If you want to find in transverse, we'll get it from 3C figure. Okay. How to refer, like if I have a figure 4C, it depends upon a factor beta. Okay. So beta, if you remember, we saw in the first chapter, is nothing but is the ratio of RO, which is the radius of the nozzle, which is connected, and Rm, the radius of the shell, multiplied by 0.875. So that is a beta. So it depends upon the geometrical dimension. Okay, so we already have the geometry. So we have the beta. The second line which you see here, let me just draw it for you. So these are the line. So you can see these lines, right? This gamma 10, gamma 7.5, gamma 5. Okay. So these are the lines. Okay. For gamma. Gamma again is what? Again, a geometrical factor. Rm divided by T. Rm is the shell mean radius divided by the thickness of the shell. We have both these values. So we have gamma also. So once I have gamma and beta, from beta we'll move upwards. We'll see where we are crossing gamma, and there we'll move horizontal, and we have this value of this constant. Okay. This value will get, now we multiply with the other part of this equation, and we get the stress value. Getting it, guys? Is it making sense or becoming a little bit complicated? Come on. Are you getting it? How to refer this figure? Making complete sense. Thank you, Alim. Thank you. Okay, it's simple. If you don't try to over thinking, or it is fairly simple if you just keep it straightforward. Similarly, there is a figure, the other figure, figures 3C, which we can refer for the circumferential direction. Okay. So by referring this, we'll get the constant. Okay. And then we'll talk about how to get the, if we just use the formula, let us see how we'll do that. So what we are trying to calculate, circumferential membrane. Okay. The load is P. Okay. Figure 4C or 3C. Curve N5 P by Rm, that is the value of that constant, and this is the formula. So this value, that which is written under curve, we'll getting from the curve. This we are getting from the curve. So we have this value. If we multiply with Pm into PM divided by RM into T, we will get the value. Okay. Now that will be positive or negative. You don't have to be worried because the signs are already given by WRC. Just calculate this value and put against the sign. Okay. Great. So it's not that difficult, guys. If you just make an Excel sheet, it will be, easy. Great. Now, this is not all. What we did only we calculated a value for P load, radial or axial, whatever you call, and only in circumferential membrane. The same philosophy we have to follow and get all these values. What is this? Circumferential membrane we got. Then we'll again do the same method. We'll find circumferential bending for P load. Then circumferential membrane for MC, circumferential bending for MC, circumferential membrane for ML, circumferential bending for ML. Okay. If you remember, other loads generate only shear. So only we have to take these loads. So that is the reason MT is not coming into picture, VC is not coming into picture, and VL is not coming into picture. MT will not produce circumferential bending, Halim. Okay. Great. So these are the convention, which is right hand side. You see the signs. So you just calculate the value and put against the sign. If you make a good Excel sheet, it will be pretty easy. You don't have to depend upon software for this. So this is for circumferential stress. Remember, we have to also find for the longitudinal direction. Same table. One more table you'll have to make for longitudinal stress. Yeah, it's time taking, consuming, but repeated activity. Okay. So once you have longitudinal, now it's shear. How we'll find the shear stresses, because there were VL, VC, and MT. So you can see there is formula given for that also. And you apply that formula. There is no graph to be referred. You have the sign also. Just put those values against the sign and you have the shear stress. Now, see, till now we have just calculated the different stresses. What we'll have to do next, whether this is sufficient, like we don't know whether the loads were qualified or not. We'll have to see that, right? For that, what I need to do? I got the stresses. Lots of stresses I got. Now I will be able to club the stresses which are coming at the same point and then compare it with allowable. Absolutely right, Himanshu. Okay. So next activity, first you have to categorize them in PM, PL, and Q. Okay. PM, like I said, PM is what? Even if you don't understand PM, PL, Q, don't worry. Just listen to this. You will have a fair idea. Okay. So PM is a load, as a stress coming because of a load which is uniformly distributed and it's uniform across the section, like pressure. So because of pressure in one direction, you will have very uniform stresses. Okay. And where the point we are taking, which is away from discontinuity, there is no, like, if you remember the cylindrical stress which we calculated for circumferential and longitudinal, there was no nozzle, there is no local variation which is coming there. It's very far away from any discontinuity. Okay, remember, so that is PM. So the stress which you get because of pressure, that is PM. PL is the stress which we are calculating. These are local loads because of local stresses, because of local load. And then there is Q. Again, it's local, and that is a bending. Any stress which is coming in form of bending, that is your Q. Okay. Why we are trying to categorize them as PM, PL, and Q, that you will understand. Okay. So now, is it clear which one I'll give PM, which one I'll give PL, and which one I'll give Q? Is it clear? So if you remember that equation, N by T, the first part is PL. The second part, 6M by T square, that is what? The second part of that equation, general equation, that is Q. Absolutely right. So PL and Q is what we got from the equation. PM is already we have because of pressure. Now we'll do the summation of all. PM we can calculate by UG27. PL we have already got, and Q we have already got by this calculation. So circumferential, longitudinal, both separately we have calculated. And then once we have that and all the points, we'll see the PM value. So PM will be fairly, constant for all the points. Okay. Only that circumferential will be half. Circumferential will be more, longitudinal will be half, So based on like A will have the half of the value. C and D will be having the maximum value. So PM, the max value will take PM plus PL. Again, maximum of all the points, whatever we are getting, the maximum value will select. And the third one, PM plus PL plus Q. All three combined, what is the maximum value on all the points because of different loads, which we have calculated. We just take the maximum value. Now we'll be checking for whether the stress is safe or not. So PM we compare with allowable, S, right? So like that is already performed for us, right? That UG27, when we do the calculation, it is the first stage that is already taken care. PM plus PL, that we can go up to 1.5 times S. Now you understand why that local we are trying to separate. Okay. Local we are trying to separate because PM plus PL is having more allowable. Now why? Asif, why that local is having more allowable? Anybody can tell? Anybody can reply to that? Why that local PL is having more combined loading? So because of we are doing combination, we can allow more. Is it so, Himanshu? See, because if we're just adding, I cannot allow more load, right? Local effect. Yes. Now you are, so because these are only local in nature, we are allowing it little higher, because we know that, see, if you just break that 1.5 times S, what exactly it is? S is 2/3 of yield. So if we just break 1.5, it's 2 by 3, 3 by 2. So if we just multiply, it will become, means we are allowing up to yield. So because these are very local in nature, we are allowing it to yield. Why? Because it is local, it will not fail. It will not result into failure of that component. The local stresses are kind of secondary in nature, even though they are primary membrane stresses. But they are little bit secondary. Just try to imagine, there is a small point where that stress is very high. It will deform and it will relax its stress, right? It will not result into the failure of the component. Okay. Now the third part will be very, interesting for you. PM plus PL plus Q. The secondary is also coming into picture. You can allow up to 3S, twice more than yield. Okay, why? Q, if you remember, Q is positive and negative. If you see across the cross section, it's 0. If you do just the summation across the cross section, it's 0. Okay. So because of the secondary nature of the bending stresses, if we are adding PM plus PL plus Q, you can allow up to 3S. Still your vessel is safe. Okay. And that is the reason we are trying to segregate some loads in local, some loads in Q, so that finally, we can relate to the relative respective allowable limit. Okay. because if I compare Q with S, it will fail. Okay. And as per code, we can go up to more. If you see in 23, you will also, get this. Great. So once we are doing this, and if it is coming within the limits, your design is safe. Okay.